Spectroscopy involves the power of light in the study of nature. In a nutshell, spectroscopy is the study of how light or electromagnetic radiation interacts with matter. It involves using a narrowband light source to irradiate matter with light, and then using detectors to look at the light frequencies radiated by the matter in response. From this, and using the theory of quantum mechanics, we can learn much about the material we are studying. Spectroscopy is now used to observe the very smallest things in nature to the very largest, from atomic nuclei to the light from galaxies. And electromagnetic radiation from the lowest energy to the highest energy can be used to probe matter. Nuclear magnetic resonance uses low-energy radio waves, but the massive binding power of the atomic nucleus results in high-energy gamma-ray emission. In my career, I have used a kind of spectroscopy called fluorescence spectroscopy to study the interaction of small molecules with larger ones, like DNA and proteins. Most recently, I have studied drug molecule interactions with the cytochrome P450 enzymes. These enzymes oxidize drug molecules so your body can eliminate them. Understanding how these work is very important in the development of new drugs. The cytochromes P450 are fluorescent, and often the drugs that bind to them are fluorescent too. Thus, there are two fluorescent probes that enable us to study the interaction. One compound that is not a drug, but is a substrate for some P450s is pyrene, a compound that is highly fluorescent. And now I will turn on the lights, and I will show you the instrument that we are using to do fluorescence spectroscopy. I'm sorry as I get this moving over here. I have a sample of pyrene in the sample compartment holder for the fluorimeter. And I'm going to go ahead and take a run of this called an emission spectrum. I hit the pyrene at 335 nanometers, and I look at the light that's emitted when I do this. So I choose the experiment type, and this will be an emission spectrum. And I'll close the slits down, which let me define how much light gets to the sample and how much gets to the detector. And I'll excite at 335 nanometers, and that is ultraviolet light, by the way. And so I will start the scan at 350 nanometers, and I will go all the way up to 500 nanometers in increments of 1 nanometer. And now I hit run, and I check the detectors to make sure I've selected the right detector. I think we're okay. I run this, and we'll see the characteristic spectrum of pyrene. Pyrene is a molecule that binds to some cytochromes P450. It's not a drug itself. In fact, it's found in burning coal. It's found in burning fats that are found in foods, for example. And you can see the spectrum of pyrene being collected real time. There we go. There's the characteristic sharp line spectrum of pyrene. Most large molecules of that size, say about 4 or 500 Daltons, something like that, don't have sharp lines like that. But pyrene and other polycyclic aromatic hydrocarbons do. And in RadLab, I use this instrument as well, and I let them take spectra of pyrene. And those sharp peaks correspond to vibrational energy levels. It turns out that in quantum mechanics, not only are electronic emissions governed by quantum mechanics, but so are vibrations and rotations. And those sharp peaks at about 370 to 410 nanometers represent vibrational states of the molecule. And so I use my spectrometer not only in my research, but also in our junior-senior lab course that we affectionately and unofficially called RadLab. So that's a spectrum of pyrene. And now let me show you how the spectrometer itself works. The spectrometer has a unit down in the end where the fans are and the light is. It's a 1500 watt xenon bulb that emits a lot of light in the ultraviolet. And the light goes through in what we call an excitation monochromator, which selects the light that goes into the sample compartment. And the sample is in here. And we use special fused quartz cuvettes that don't block light in the UV. And then the light that the sample emits goes to the emission monochromator that scans the light and tells the computer how much light of different wavelengths are emitted. And here is the detector, which detects the light. It's a Hamamatsu detector. And that unit spectra acquisition is affectionately called the slave. And it's basically got the spectrum hardware that tells the spectrum what to do. And then that is ultimately governed by a computer. So that is a spectrum of pyrene. And again, I don't have the samples of the protein here, but pyrene is a substrate for cytochromes P450 because all kinds of chemical compounds that you make or that you ingest, right, are metabolized by this suite of enzymes so that your body can eliminate them. So although a physicist, I'm trained as a biophysicist and also to some degree as a chemist. And so now what I think I'm going to do is I'm going to put a sample, let's see if I can get this to work here. And I'm going to put a sample of cresyl violet in the spectrometer. Let's see if that will work fine. I have to have gloves on before I do this. Okay, so I will take the pyrene sample and take it out of the cuvette. And I will rinse it with methanol to get rid of the pyrene. The pyrene is highly fluorescent. Fluorescence spectroscopy is a very, very high sensitivity technique. We can get down into the nanomolar and picomolar rather easily. And so I'll rinse this out several times. Now, I'll put the cresyl violet sample in there. Okay, so let's see. I don't know if you see me there. Maybe you can. But I'm going to go ahead and select another experiment, and this will be an emission experiment. And I'm going to excite at 350 again, and excite from 365 up to 700. So that encompasses really all of the visible light spectrum, which is about 400 to 700. And I'm going to collect this, I'm going to do this with 3 nanometer slits. I'm going to close down some of the light getting into it. And I'm going to run and let's see what we get. I'm not sure what we'll get. Well, we're getting something for sure. There might be a little bit of residual pyrene in there. I'm not really quite sure. Well, it looks like we do have some cresyl violet. Oh, there's another one. Oh, that's another large peak. Okay. So there is an enormous cresyl violet peak, and that's what the spectrum of cresyl violet looks like. Most molecules don't have the sharp spikes that pyrene has. It's harder to see the vibronic structure. And there we go, that's cresyl violet. So taking fluorescence spectra isn't too laborious or time consuming. The main issue is getting rid of contaminants out of the solution and interpreting them. Interpretation of fluorescence spectra can be a bit tricky. So I'm going to go ahead and end this soon. I want to welcome anybody watching this. We'd love to have you at Grove City College. We'd love to have you in the department. And I, as well as all of my colleagues, would enjoy being able to mentor you doing research. So thank you for paying attention, and you all have a great day. Bye-bye.